Functions are reusable blocks of code. They usually have some inputs, usually perform some sort of process, and usually have an output. We've been using a function called main to run all our programs and examples so far. This is a special function that is called as the program starts. We've also used a few other kinds of functions and methods, special functions attached to data types that are built into Rust. We can make and use our own functions too though. This series has a free accompanying book in which you can find all the details for this tutorial. Check the description below. My name is Daniel. Welcome to Iris. Functions can be pure or impure. A pure function takes 0 or more inputs, does some processing, and returns 0 or more outputs. This makes the function extremely predictable. Given the same inputs, they will always produce the same outputs and nothing else within the system will change. An impure function, though, might not always produce the same outputs given the same inputs, or may have side effects within the system, either changing something else in the system or having some other part of the system change what that function does. We'll learn more about this in a little bit, but first, up to now, we haven't needed to change any data once it's been created. By default, all variables in Rust are implicitly immutable, meaning that the values inside them cannot be changed. This, for example, won't compile. We get an error that we can assign an immutable variable, but we can't change it. Immutability is good because it prevents data from being changed by mistake, which, going on the name of the variable in this example, seems like it's what's happened here. It doesn't seem like 1 should contain 2. So we should try to use immutable variables as much as possible, but software is all about processing data. If we could never mutate values, we'd always have to depend on creating new values, which is fine for small data, but imagine we're processing large data like an image. Do we want to copy it every time we make a single pixel change? You can explicitly opt into mutability by adding the keyword mut, M-U-T, in front of the variable name. Functions are defined with the fn keyword, short for function, followed by a name, followed by brackets, which may or may not contain parameters, possibly followed by an arrow and a return type. If no return type is specified, the return type is the unit type. See our video on data types to learn more about that. This part of the function is called the function header. The function is completed by a code block, that's code between curly brackets again, which is called the function body. Let's create the simplest possible function. This function is called sayHello. It has no parameters and does not return anything. Because it writes to the terminal, this function is considered to be impure. We can call the function using its name and empty brackets inside our main function. Let's get a little bit more advanced and give our function an input. Inputs to functions are called parameters, and they live between the brackets in the function header. We'll add a parameter called name and specify that its type is a reference to a string slice. After that, we can use it like it's a variable inside the function body, so we'll use it in our print line. Now we just need to update where we call our function to pass the parameter. As ever, we'll use my cat's name. We can have multiple parameters too. Parameters are ordered, so when you call the function, you need to match the order that they're specified. Let's make a new function that greets 2 people. In Rust, all parameters must be used when calling the function. Next, we're going to move the side effect out of our function. Instead of directly printing to the terminal from the function, we'll return the string that we want to display and move the side effect to main. We'll rename the function to reflect the change in behavior. We'll add an arrow and the return type, in this case string, to the function header. We'll create the string using the format macro and store it in a variable message. We'll return the message from the function. Remember that code blocks can be expressions. We don't need to explicitly write return, though we can. We just need to make sure the thing that we want to return is the last bit of the block and forego the semicolon. We'll update the call site of the function to set the variable greeting to the result of calling the function. Then we can use that variable in a print line in the main function. Now we have a pure function that takes an input, processes it, and returns an output. As with most languages, in Rust, functions can call other functions, like how our main function called our createGreeting function in the last example. A function that calls itself, though, is described as recursive. Take for example this function, which will find the nth number in the Fibonacci sequence. A quick side note, this function uses a Boolean OR in the if, so the larger expression evaluates to true if either the left or right parts of the expression evaluates true. We also use the if-else as an expression, so the return value of the function is equal to the value from the if-else blocks. If the expression in the if is true, then we return n, otherwise we return the result of calling the same function with new parameters. Because we call find Fibonacci inside of find Fibonacci, this is a recursion. Each time we call the function this way, we add another layer on the stack. The stack is finite, so if we give the function a large enough number, it will eventually run out of space in the stack, causing a stack overflow. And you'll see something like thread main has overflowed its stack. For the advanced programmers watching, Rust does support tail recursion, which is a technique for turning a recursive function into a loop at compile time. This not only minimizes stack usage to effectively a single function call, but it's also much faster. However, I think this is an overrated feature. In any language that supports tail recursion, it's hard to guarantee that the compiler will optimize in this way, and it's easy to break. My recommendation is that if you need to recurse a lot, then consider whether you can rewrite your function as a loop instead of depending on a compiler optimization. Data in Rust has to live somewhere in physical memory. This primarily comes down to the stack, the heap, and the binary. For a deeper explanation on those, see our video on memory. The heap specifically can be thought of as managed. You ask the operating system to allocate you a block of memory to use for writing to and reading from. Once you're finished using the block of memory, you free it and return the memory to the operating system. In some programming languages, this process is manual. You have special commands for asking for memory to be allocated and special commands for freeing it. This leads to some problems though. What happens if you try to use memory that wasn't allocated? What happens if you try to use memory that you already freed? What happens if you try to store more data in there than fits into that allocated block? It's surprisingly easy to make mistakes here. We're all human, but the consequences can be severe. Around 70% of all security vulnerabilities today are caused by accidental misuse of memory. In order to get around these problems, some programming languages use an automated method of memory management called garbage collection. In this method, you, the software engineer, don't have to think about the actions required to allocate or free memory. Instead, as memory is allocated, the garbage collector built into the language will monitor to see which parts of your program are actively looking at that bit of memory through a process called reference counting. Once the number of places using that data, the reference count, has dropped to 0, the garbage collector can safely free the memory. This is much safer than manually managing the memory yourself, but comes with some of its own problems. The garbage collector requires additional resources in order to do the management. This includes CPU time to do the work, but in some cases it can also require significantly more memory. Managing memory by proxy is less efficient than managing it directly, meaning that it's slower. And you have limited to no control over what the garbage collector does or when it does it. This can have big negative impacts on performance at completely uncontrollable times. Rust's method of memory management, ownership, is a little bit different. It's low level, giving you the speed of manual memory management, but its mechanisms are hidden behind abstractions that mitigate those risks. It's certainly not as easy to learn, but once you get your head around it, it makes a lot of sense. In Rust, all data is owned. When the variable that owns the data goes out of scope, the data is dropped. This means that if the data was stored on the heap, then that bit of memory is immediately freed. Let's have a play with this. First, let's have a look at the scope aspect of ownership. Here we create a variable A in what we'll refer to as the outer scope. Then we start a new code block which creates a new scope we'll call the inner scope. We can use A in the inner scope just fine, as the inner scope is part of the outer scope. We can create and use a new variable B in the inner scope too. However, when we close the inner scope, A will still work as we're still in the outer scope, but B is no longer available. Once a variable is out of scope, it can't be used. If we try to compile this code, in the error output it tells you cannot find value B in this scope and what line we tried to use it on. It tells us exactly what's wrong. Rust's compiler messages are generally amazing, especially when it comes to working with ownership, so it's worth getting used to how Rust presents its errors. Next, let's look at how data can only be owned by one thing at a time. We'll create a string and put it into our A variable. Then we'll assign A to B. After this point, we can no longer use A. If we try to compile, we'll see the error value borrowed here after move. The statement let B equal A moves ownership of the string from A to B. Normally, we wouldn't move data in this way. Spoilers, this is after all a video on functions, but it neatly shows us that data can't be owned by multiple variables at once. What does Rust mean by move though? You might have noticed that we swapped from using chars in the first ownership example to a string in the second. This is because there are two mechanisms at play, move and copy. Let's try the same code with chars. This time we set A to a char, and now the code works. Why didn't it with string? The reason for this is that char is copy. That is to say that it has the copy trait. We'll talk more about traits in a future video, but essentially traits provide behavior to data and data types. Things can have the copy trait applied to them if they can be trivially copied, and this usually, always, means that data exists on the stack. The reason for this is that all that allocating and freeing on the heap that we talked about earlier requires a non-trivial amount of time and resources. When data has the copy trait, instead of being moved from one variable to another, it's copied. This mechanism on data that has the copy trait is implicit. Data that does not or cannot implement copy may still be duplicated if it implements the trait clone, which provides the clone method. A method is a function that's attached to some data or data type. We'll talk more about methods when we talk about traits in the future. This mechanism is explicit in that you have to call clone yourself. String already implements the clone trait, so let's use that to duplicate the data in our A variable instead of moving it. This now works too. You'll also note that we used a full fat string here, not a string slice reference. Here's what that would look like. As you can see, it also works. Because hello exists inside of the binary's data, you can't own it, at least not in the same way. Ownership would imply that once it's no longer used, it can be freed, but as it's part of the binary, that wouldn't really make any sense. Instead, we just get a reference to where the value exists in memory. This reference is also immutable. You can't change values in the binary. Immutable references, though, are copies, so setting B to A is a copy instead of a move. But what do move semantics have to do with functions? When we pass data into functions through the use of parameters, the data follows the rules of move semantics. Let's go back to our createGreeting function. Instead of passing in a string slice reference, what would happen if we passed in a full fat string? In this example, we move ownership of the data stored in the variable uKey into the parameter name. This means after the function, the variable uKey can no longer be used. Because the format macro does not take ownership of the data in name, we could return both the message and the original string data using a tuple. Let's change the createGreeting function to return a tuple that includes both strings. When the function returns, we destructure the tuple, see the control flow video for more on that, into two new variables, message and uKey. A quick note, this new uKey variable is a different variable from the old uKey variable. This is called shadowing. Unless you were doing this inside an inner scope like we were doing earlier, this is functionally meaningless, but I think it's interesting. Anyway, this is obviously a terrible way to deal with ownership. We don't want to have to pass ownership back and forth just to use functions. Going back to our original function, you can see that we were taking a reference to a string slice instead. The full fat string type can be dereferenced into a reference to a string slice. Remember, the internal representation of a string is the same as a string slice. So we can create a reference to our full fat uKey string using an ampersand. Let's say we wanted our function to modify the string instead. Ideally, we don't want to modify data that's passed to a function, but sometimes that's not possible. If you need to do it, you can pass a mutable reference. In order to mutate greeting via a mutable reference, the variable greeting must itself also be mutable. When we pass the reference, we are explicit that we are allowing the reference to be mutable too. The function takes a mutable reference to a string, not a string slice. String slices are not mutable, but strings are. Before we move on, one last note about references. You can have as many immutable references to a value as you like, or you can have a single mutable reference. Immutable references are copy, but mutable references are not. So far, so clear, but it turns out that keeping track of all of those references is actually quite hard. Let's create a function that takes a reference to a string and returns two parts of that string. In order to do that, we'll also take a point at which we're going to split the string. We're going to make sure that the point is never greater than the length of the string in bytes. Then we'll split the string in two at that byte, starting at 0. To do this, we use a range to take a subslice. We discussed half-open ranges last time, but this means starting from the beginning of the input up to, but not including, the uptooth byte. And this means starting from the uptooth byte and continuing to the end of input. Also remember that because we're using bytes here, there's a bit of a risk that we could split the string in the middle of a character. Ideally, don't do it this way. The left and right parts of the split are returned in the tuple, which we immediately destructure. The awesome thing here is that the string isn't duplicated. The values left and right are references that point to the inside of our original input string. How does Rust know that though? Let's try confusing it a bit. Instead of splitting at a particular point, we'll find a substring inside the input string, then split around that. This example won't compile. We get the error expected named lifetime parameter. What does that mean? We also get guidance from the Rust compiler on how to fix our problem, and what it suggests will work, but once you understand the problem, you'll see there's a better way to solve it. A lifetime is Rust's way of tracking reference usage. A reference needs to be tied back to its owning variable, and this relationship must be understood at compile time. Let's tie what we know about ownership to what we know about the stack and heap. Some data is stored on the stack, some is stored on the heap. As we enter a function, all the space required for the stack data is added to the top of the stack. Heap data is tied back to variables on the stack that own the heap data. Further functions go up the stack. As functions come to an end, they are removed from the top of the stack. Owned data that is not returned down the stack is freed. When it comes to references, we need to make sure that a reference to owned data does not outlive the owned data. For example, let's create a string on the heap called myString. We'll return a reference to that string, but not the string itself. This would mean that when the function comes to an end, the variable myString goes out of scope, so the data that it owns on the heap is freed. What would happen if we used the returned reference now the data that it references has been freed? Luckily, Rust won't let us do this. In order to prevent this, Rust tracks the lifetimes of each reference and its owned data. It can often do this automatically. In the first version of our function, Rust can see that only one reference enters the function, no other references are in play, and so Rust knows that the two references that are returned must be tied to the same data as the incoming reference. In the second version of our function, we passed two references in. Now Rust is less sure about which data the returned references should be tied to. The suggestion the Rust compiler gives us is to tie all the references to the same lifetime. This actually is a valid approach, as Rust will use the shortest living bit of data to tie the references to. Let's do what it says. Rust lifetimes are annotated with generic labels. Remember labels from the last video? If we were being lazy, we might use a single lettered label like A, though if a lot of lifetimes are at play, it's definitely better to use longer, clearer labels. We'll change the header of our function to include the lifetime A. First, we tell Rust we want to use a lifetime by putting it inside triangle brackets after the function name. Then we mark each reference with that lifetime. You can run the above and see this example works just fine. However, it's not ideal. We've tied all the references to the same lifetime, which Rust interprets as whatever dies first. Using a contrived inner scope again, we can create code that doesn't work. We've confined our substring to the inner scope. When the inner scope ends, that data is freed. You and I know that left and right references are tied to the input variable in the outer scope, but we told Rust that it should tie all the lifetimes together. Since the substring lasts the least amount of time, that's the lifetime that's used. So when we try to compile, we get borrowed value does not live long enough. To fix this problem, we can either give the substring a different lifetime annotation, for example b, or just remove the lifetime annotation from the substring parameter. Now everything works as expected. References and lifetimes get really tricky. They're probably the hardest part of Rust to learn. Here's how I like to think about them though. Imagine a person flying a kite. The person is the owner of the data, regardless of where the data is actually stored. The kite is the reference and the string or kite line tying them together is the lifetime. The kite can go up and down the stack freely, but it can't go below where the person is standing. That's our equivalent of the ground. Multiple people can fly their kites through the same functions and each one gets its own kite line or lifetime. It's even possible to entwine the kite lines. Imagine a function that takes two references to a string and returns the longest. This is like a function that accepts two kites, but only the largest kite is returned. Because you don't know who that kite belongs to, it can't go below the person standing on the highest point on the stack. Lifetimes can be incredibly powerful. There's no need to fear them. One amazing example is that, say we have a string that contains some complex data. For example, it could be a serialized format like JSON or YAML, or it could be something like an advent of code input string. Lifetimes mean that you could bring that string into your program, allocating the memory for it just once, then turn it into a complex data structure. So long as the original string exists, the data structure need not allocate any further memory, which is incredibly efficient. Here's an example with a user struct that has two properties, both of which are references to string slices. The data for this struct is in a string. When we pass the string, it can return a new user where the references are both tied back to that original string. So here's my list of best practices when it comes to working with functions. Create a function whenever a section of code can be described in just a few words. The function name should always describe what the code is doing. Functions should only do one thing, avoid big branches inside of your functions. Keep functions short, but not too short. Functions should be a set of instructions grouped together. Too few and it may not have been worth creating the function, too many and maybe you need to break that down into more functions. Do not take ownership unless you expressly need to own some data, but also try to avoid mutable parameters. Finally, be specific about your lifetimes. If using more than one or two, try to name them something sensible. How did you get on with your control flow homework? Here's my FizzBuzz program. I created a range 1 to 100. Note the equal sign to make sure that 100 is included in the range. I used that in a for in loop, and then inside the for in loop I used a match statement with match guards to check whether the number was divisible by 3, 5 or both, and then I printed the relevant output. Did you manage it in a different way? If so, let me know in the comments. This time I'd like you to create a function that splits our string like before, but instead of returning a left and right side, it splits every part of the string. There's already a split method on string slices, but I'd like you to only use find and create a recursive function. You'll need to use a collection type to store all the chunks created by the split. I suggest using vec, which is built into Rust's standard library. A vec is a variably sized array that you can push new items onto the end of using the push method. To check whether your vec contains the correct information after the program is run, use the debug macro, dbg. We'll talk more about how this works another time. All you need to know is that it will work for a vec of string slice references. The header of your function might look something like this, but I'm not going to tell you what the lifetime should be. If your main function looks like this, then your output should look like this. This isn't an easy task and will require thinking about the lifetimes carefully. If you get stuck, feel free to ask for help in the comments. Next time, we're going to look at another of my favorite Rust features, the built-in test tools. We'll We'll also take our first little peek at modules and conditional compilation, which is, I'm afraid, both way easier and way more boring than it sounds, but testing in Rust is awesome, I swear. After the next video, we're also going to change the way that we talk about Rust, so don't miss out. If that sounds interesting, don't forget to like and subscribe. Do let me know how you get on with your homework, and I'll see you next time. This is much safer than manually managing the memory yourself, but comes with some of its own problems. Manually managing the memory, manually managing the memory, manually managing the memory, manually managing the memory, manually. Here's how I like to think about them. Imagine Wibble Wobble. Hey buddy, are you knocking over my camera? Is this in protest of you not being in? Come. Oh buddy. Here you are. Let's say hi to the people. Gosh, you're a white blob in these lights, aren't you? Is it too bright? Well, it's not time yet. What do you mean, huff, huff, huff? Have I got to stop, feed you, wait 20 minutes for you to finish? Meow.